Hello students, कैसे हो आप सब? Welcome to class. Today we're diving into Unit 13, Nuclei. Now I know this chapter can feel a bit intimidating, but trust me, we're going to break it down so simply you'll have zero fear, and everything will be perfectly exam safe. You're about to find out that the tiny core of an atom is one of the most fascinating things in all of physics.
So, what's on our plate today? Let's have a quick look. We'll start with a puzzle. I call it the impossible nucleus. Then we'll uncover its secrets, the strongest force in the universe, and the mystery of the missing mass. After that, a very, very important section on exam silent killers to make sure you don't lose any marks. And finally, we'll tie it all together with a summary. Ready? Let's begin. All right then, let's start with a genuine mystery. You know, the nucleus is something that, based on all the physics you've learned so far, shouldn't even exist. It's like a tiny explosive puzzle sitting right at the heart of every single atom. Now, here's where it gets really interesting. We all know Coulomb's law, right? It's a fundamental rule. Like charges push each other away. Simple. But the nucleus is absolutely packed with positively charged protons. So the big question is, why doesn't it just explode? Why doesn't it all just fly apart instantly?
Just look at this. All these protons, all positive, are squeezed into this unbelievably tiny space. The electrostatic force, the Coulomb repulsion trying to tear them apart, is absolutely enormous. We're talking trillions and trillions of times stronger than gravity. By all logic, this thing should be impossible. But it's not. It's stable. So clearly, something else must be going on here.
And just to give you a sense of the scale of this problem, think about this. The nucleus is about 100,000 times smaller than the whole atom. To put that in perspective, if an atom was the size of a giant cricket stadium, the nucleus would be like a single grain of sand in the very center. And yet, that one tiny grain contains almost all the mass of the entire stadium. This just makes the puzzle even stranger, doesn't it?
Okay, so what's the solution to our impossible nucleus mystery? Well, to figure it out, we need to introduce a new character to our story, a new, incredibly powerful force that acts like a secret, super strong glue.
And to understand this new force, let's use a simple analogy. Just imagine all the particles inside the nucleus, the protons and the neutrons, are people crammed into a very, very small room. So, inside this crowded room, the protons are like people who really don't like each other. They're constantly trying to push each other away. That's our Coulomb repulsion. But there's another force at play. Think of it as a super strong friendship force that only works when they're practically touching, shoulder to shoulder. This friendship is so powerful that it completely overpowers their dislike for each other and just glues them together. This is the strong nuclear force. Now, this comparison table is absolutely crucial for your exams, so pay close attention. The Coulomb force, you see, it has an infinite range. But the strong nuclear force, it's a short-range specialist. It only works inside the tiny nucleus over a distance of about 1 femtometer. That's 10 to the power minus 15 meters. Also, it acts on both protons and neutrons, and most importantly, it is the strongest of the 4 fundamental forces in nature. You have to remember this. But believe it or not, the strong force is only half of the story. There's another incredible secret that the nucleus is hiding. And this one involves missing mass and probably the most famous equation in the history of science. But first, let's get our basics right. For your exams, you must write these definitions exactly as they are here. The atomic number, Z, is just the number of protons. The mass number, A, is the total count of protons plus neutrons. And together, we call these particles nucleons. And this is the standard notation we use to represent a nuclei. Okay, get ready for a big surprise. Let's say you take 2 protons and 2 neutrons and you weigh them all separately. You'll get a certain total mass. But then, when you weigh the actual helium nucleus that they form, it's a little bit lighter. The final nucleus weighs less than its individual parts. So, where did that mass go? Did it just disappear? This difference, this missing mass, has a special name. It's called the mass defect, and its symbol is delta M. As per the NCERT definition, it's the total mass of the individual nucleons minus the actual measured mass of the nucleus. And this tiny bit of missing mass, well, it's the key to understanding the incredible energy that holds the nucleus together. And the explanation? It comes from the great Albert Einstein. You see, the mass wasn't destroyed. It wasn't lost. It was converted into a tremendous amount of energy, according to his legendary equation, E equals mc squared. And this energy, we call it the binding energy.
It is the energy glue that holds the nucleus together. It's the energy that was released when all those nucleons first came together to form the nucleus. And it's the exact same amount of energy you would need to pump in if you wanted to break that nucleus apart again.
Let's make this crystal clear with a super quick example using helium-4. It's a simple 3-step recipe. Step 1, you find the total mass of 2 separate protons and 2 separate neutrons. Step 2, you subtract the actual mass of a helium-4 nucleus from that total to find the mass defect. And finally, step 3, you just convert that mass defect into energy using E equals mc squared. Simple as that.
And when you do the calculation, the answer you get is about 27.3 mega electron volts. Now, that number might not sound very big, but for a single tiny nucleus, that is a gigantic amount of energy locked away. This right here is the fundamental secret behind nuclear power.
Okay, everyone, full attention here. This section is what I call the exam silent killers. These are the silly, common mistakes that so many students make, and they can cost you precious marks. Let's make absolutely sure you are not one of them.
First big mistake. A lot of students get confused and think binding energy pushes things apart. No, it's the complete opposite. Always remember, binding energy is the glue. The more binding energy a nucleus has, the stronger the glue, and the more stable the nucleus is. Higher binding energy is a good thing.
And the second killer, never, ever, ever write in your exam that mass is destroyed or lost. It is not. Mass is converted into energy. The total amount of mass energy in the universe is always conserved. It just changes its form. This is a very, very crucial point. Please don't forget it.
Okay, let's bring it all home now. We'll do a quick summary of the most important points and see how this all connects to the bigger picture of physics.
So, when you're revising, just lock these 4 points in your mind. 1. The nucleus is tiny and incredibly dense. 2. The strong nuclear force is the superglue holding it together. 3. The mass defect gets converted into binding energy, thanks to E equals mc squared. And 4. The higher the binding energy per nucleon, the more stable the nucleus is. That's it. Simple.
And why does all this matter? Well, because this isn't just theory for your exams. Understanding these basic ideas is the key that unlocks so many amazing things, from radioactivity and how nuclear power plants work, to the incredible fusion reactions that power our sun and every single star in the night sky.
And all of this leaves us with one final, powerful question to think about. We've seen that forming a nucleus releases energy, so it stands to reason that we could also get energy by either splitting very heavy nuclei apart, which is called fission, or by forcing very light nuclei together, which is called fusion. And that simple idea, well, that's the gateway to our very next topic.